G'day YouTube, Warbles on a lot here. Welcome to the second part of my in-depth little warble series about Sopwith camels. Those of you who watched part 1 will be aware that part 1 and part 2 are based heavily on text written by Wing Commander Norman Macmillan in Great Aircraft, published in 1960. Part 1 being Popping Firecracker. Today's video, Ubiquitous Fighter. Once again, I will read from the prepared photocopy, and because this line drawing and this black and white photograph captioned Sopwith Camel F1, contemporaneously called a Scout, was a single-seat fighter, comprise the only illustrations of Sopwith camels in Captain Macmillan's otherwise brilliant book. So I won't be hesitating to dip into my stash of Sopwith camel photos in various reference books, which I have collected over the years. Chapter 6, Camel, Ubiquitous Fighter. As twixt two equal armies, fate suspends uncertain victory. From The Ecstasy by John Donne. The Camel was one of those lucky strikes that turned up sometimes among the varied products of aircraft manufacturers in those unpredictable days when science had not quite overpowered art in the drawing office, and an aeroplane could still be built from the drawings chalked on the wall or the floor of the erecting shop, and a prototype might fly only 3 months after the conception of the design in its creator's mind. There was nothing very unusual about the construction of the Camel. It conformed to the practice of its time when aircraft factories smelt deliciously of clean timber and the sawmill. Its fuselage had 4 ash longerons, square in section and curved lengthwise, to the outlines of the body, which was shaped, either in side or plan view, rather like a coffin. These longerons and 8 sets of square section spruce struts, each set containing 2 side and 2 cross struts of the correct length, were the timber components of the fuselage girder. The struts were located on the longerons by steel plates, through whose eyelet holes piano wires were reeved for the internal and top and bottom cross bracings and the side bracings. Each wire was tensioned by a turnbuckle. By correctly adjusting these turnbuckles, the riggers trued the fuselage into correct alignment. A steel vertical rudder post accepted the merging bottom longerons at its lower end, and its upper end similarly accepted the merging top longerons, which here were reinforced by the wood mounting base for the tailplane. By its nature, a rotary engine overhung its mounting. This demanded a good cantilever installation. In the Camel, the one-piece longerons were continued forward from the first set of struts already mentioned to form the engine mounting bay. Their front ends were interconnected on each side by a vertical wooden strut. Steel fittings on a 3/4 hoop of steel tube that curved over the flat sides and top of the fuselage girder, but not underneath it, linked all 4 longeron ends to this hoop. To this assembly was added the front engine mounting, a steel plate in the shape of a St Andrew's cross, but with a central hole, and the centres of the arms cut out for lightness. In place of the side bracing used further aft, the engine mounting bay was strengthened by a stout wooden strut running diagonally between the front lower corner and the rear top corner. To curb elasticity further, these diagonal struts were braced with fore and aft cross wires and laterally by protruding kingpins and wires. The rear steel mounting plate for the engine bolted to these diagonal struts ran centrally across the fuselage within the bay. The rotary engine was mounted in the aircraft by two circular steel plates carried on the rear hollow extension of its fixed crankshaft. The circles of bolt holes on these plates coincided with those on the two steel mountings in the fuselage. Okay, I know it's rude to point, but these are the holes there, and I think there, perhaps around there, but those two steel plates, they hook on a large plate, bolts into that circular hole there, and in that cross member there, there's a circular, well, there's a vertical support in the centre which can't be seen because of that strut in the way, and the little end bolts onto there. I think that's how it goes. Never having laid hands on an actual Camel, a reproduction replica pup with the wrong engine was as close as I ever got. A simple block tube carburettor was mounted on the open rear end of the crankshaft. Petrol was fed through a fine adjustment to a jet at one side of the carburettor. From the opposite side, a throttle slid across the opening with a tapered needle projecting in front. This needle altered the flow of petrol through the jet as the throttle setting varied. By manipulating his throttle and fine adjustment levers, the pilot controlled his engine and compensated for varying altitude. By bad handling of these controls, it was quite easy to stall the engine at takeoff or in a manoeuvre, and the novice needed careful tuition in their use. The carburettor sealed the end of the crankshaft and drew its air from both sides through a cylindrical gauze filter just behind the throttle. Rubber connections carried aluminium extension tubes across the fuselage to draw air from the outside. The open ends of these intakes are always visible in side views of the Camel, one on either side of the aluminium cowling just ahead of the pilot's cockpit. The other one, of course, is for empty cartridges and spent links to come out from the guns. These aluminium air intake extensions were the bane of long-legged pilots whose knees fouled them when their feet were on the rudder bar. I have known pilots posted to fly Camels at the front who could not operate the rudder properly because the air intakes obstructed their leg movements, and they had to be sent to squadrons flying bigger machines, such as DH-4 reconnaissance two-seaters. I have also seen legs broken in Camel crashes by these same intakes, which could not have been more efficiently placed to break the tibia and fibula. The mixture of petrol and air was carried through the hollow crankshaft into the crankcase. Petrol air mix coming down from the carburettor into the crankcase, where it was mixed, heated and partly compressed by the rotating engine and its reciprocating pistons. Thence it was carried to the inlet valve in each of the 9 cylinders through copper induction pipes. There we have the copper induction pipe. There we have the copper induction pipe. There we see the copper induction pipes on a Lerone. Somebody's taken them off that Clerget. And there we see the pipes on an 80-horse Lerone. Oopsie. The induction pipes are on the Clerget, but they appear to be the cast aluminium variety, and you can only see 2 of them because the other 7 are behind cylinders. My mistake. Both inlet and exhaust valves were mechanically operated in the Clerget, Lerone and Bentley engines. The exhaust gases discharged straight into the air, up there. The engine was lubricated through the hollow crankshaft from an oil pump mounted on the back plate. There's the pump. The oil pump mounted on the back plate, as the larger front mounting disc was named, and driven by the rotating engine through gears. And that's where the gears are. There was no pressure gauge on the instrument board in the cockpit, merely a pulsator glass. A small glass dome within which the pilot could see the oil pulsing with each stroke of the reciprocating pump, thus knowing that his lubricating system was working. Oil leads conveyed the oil to the various working parts. And here we see an oil spray nozzle. We see more oil coming up through the hollow crankshaft, and it just gets pumped into the crankcase. And an oily spray within the crankcase protected cylinder walls from deterioration due to petrol vapour. Because of the mixing of the petrol and the air in the crankcase, it was necessary to use an oil which did not readily combine with petrol, and so would maintain its lubricating properties unimpaired. For this reason, rotary engines were lubricated with pure castor oil. The common fuel and oil system and the centrifugal force generated by the rotating engine drove an exceptional volume of oil into the cylinders. Some of this oil passed the oil and gas retaining obturator rings, one of which was fitted to each piston, and then escaped through the exhaust valves into the air, half burnt. So these engines were wasteful of oil. They consumed usually about 2 gallons an hour, and their aircraft flew scarcely 50 miles to the gallon of oil. But they continued to be used because they were light in weight and easy to fit, and in the pressure of war there were not enough of any other kinds of engines to replace them. When taking off, landing and taxiing, rotary-engined aircraft filled the air with the bittersweet fragrance of half-burnt castor oil, like which the world knows no other odour. Indeed, rotary-engined aircraft, when coming down to alight or when taxiing, often trailed a blue mantle of hot, oily vapour. Most of these engines would not run slowly without stopping, so instead of throttling down, the pilot intermittently thumbed on a spring-loaded press-button ignition switch on the handle of his control stick, shown there, and again there, and also there. Note that because this particular aeroplane lives in a museum, it doesn't actually have any triggers fitted. Those are the hinge points for the gun triggers, a feature which the artist has faithfully reproduced. Returning to Macmillan, pressing this switch stopped the engine from firing. Releasing it allowed the engine to start firing again. By switching his engine off and on, the pilot controlled its average speed, and thus reduced the thrust of his airscrew and altered his flying speed and angle of glide to suit his judgment when landing, and his taxiing speed on the ground. When this thumb switch, commonly called the blip switch, was used, pilots were said to be blipping the engine or blipping into land. There was a great art in blipping, but however it was done, the procedure always increased the volume of hot oil thrown into the air, thus creating the blue mantle. Wherever rotary-engined aircraft flew, especially those with gnome monosoupape engines, that's French for one valve, which had no throttle at all, oil splashes fell from them. White tents about their airfields were soon mottled by patches of oil, as if camouflaged. Pilots who flew such aircraft necessarily inhaled castor oil fumes and were absolved from any need to take aperient salts in the mornings. But this effect was not drastic, as has sometimes been averred by writers (and talkers) who never ever flew them. Bit of a side note here. For the benefit of people who are not aware of the bowel fetishes, fixations and habits of the average Edwardian, what he was saying was that even though you were breathing castor oil, it didn't give you diarrhea, although a lot of people have written stories about that. The Edwardians and the Georgians were fixated about their bowel habits because they ate pretty much nothing but starch and decomposed meat, and they tended towards constipation. And before antibiotics were invented, getting constipated could lead to a bowel obstruction, which led to a dangerous operation with about a 50 or 60% death rate to try and clear the obstruction. So they lived in constant fear and tremor and trembling of becoming constipated. So a lot of them every day had a teaspoonful of castor oil to lubricate their innards, so to speak. They were also too polite to talk about it in public places. But that's what that sentence meant. Okay, now you've got the key. Pilots who flew such aircraft necessarily inhaled castor oil fumes and were absolved from any need to take aperient salts in the mornings. But this effect was not drastic, as has sometimes been averred by writers and talkers who never flew them. Aperient salts, read Epsom salts. Upset the electrolytic balance of your intestine and you will develop diarrhea and wash away the obstruction caused by eating stodge. The rotary engine's magneto was mounted on the backplate. Through gears, it was driven 2¼ times faster than the engine. A high-tension lead carried the spark to an insulated brush holder in the backplate. The brush holder passed the current to a distributor mounted on the rear end of the crankcase thrust box. This distributor revolved with the engine, and the position of each terminal was in line with the sparking plug screwed into the side of each cylinder head. A fine brass wire carried the spark from distributor to plug. Now, there's the wire there, and there's the wire there, depicted in the diagram. The wires will emanate from in front of that shield and behind the back of the crankcase and come out there. Same there. And here you see them emanating and running to this. The engine has 2 plugs per pot. Single ignition, twin plugs. Ideally, only one of them is going to get clogged up with oil. Not infrequently, these fine wires broke, and this caused the engine to misfire. Indeed, it is surprising that they did not break more often than they did, as they too revolved with the engine. The quickest way to immobilize the aircraft on the ground was to unfasten the inspection panel in the metal side cowling and pull the high tension lead off the brush holder in the backplate. I have seen considerate flight sergeants do this when they thought it wiser not to allow a pilot, slightly inebriated after some jollification, to fly. Imagine flying that drunk. The fuselage was divided into 9 bays with 8 sets of struts between the engine mounting and the rudder post. For the convenience of riggers, the engine mounting was called number 1 and the 8 succeeding sets of struts were numbered 2 to 9. The V undercarriage legs were attached to steel fittings at the longeron and base of numbers 1 and 3 struts. The lower wings were attached to fittings at the base of numbers 2 and 4 struts. Between numbers 3 and 5 struts, fore and aft transverse wooden members provided the foundation for the pilot's wicker seat, and behind it the main petrol tank. The top deck of the fuselage, from slightly ahead of number 2 strut to number 5 strut, was made of plywood, whose forward part was the hump, succeeded by the cockpit opening, after which the coaming sloped downwards towards the tail. In this rear portion, 2 circular holes gave access to the petrol filler caps of the 5-gallon gravity tank, seen here, and according to different makers, a 20 or 21-gallon main tank. Petrol was forced from the main tank to the carburettor by air pressure generated initially by a hand pump, there with a handle, and in flight by a pump mounted on a centre section strut and driven by a small wind-driven propeller. From number 5 strut aft, transverse plywood formers and longitudinal spruce stringers carried the graceful curve of the top deck, begun by the plywood coaming rearward of number 9 strut. The engine mounting bay contained the oil tank, which variously contained from 5 to 6 3/8 gallons in different models, and the gun magazines. You can just make out the oil filler cap there and the oil tank there and the ammunition canister and belt. This bay was enclosed by aluminium panels front, top, sides and bottom, with large oval and quickly detachable servicing panels on each side. The transverse air intake tube apertures were just behind these detachable panels. The starboard side panel fitted over the chute for discharging used cartridges ejected from both guns. Spent cartridges mostly fell on the starboard lower wing, but their drumming on the fabric was deadened by the chatter of the guns firing. The second and third bays were covered with plywood. Aft of the plywood, fabric covered the fuselage. The fuselage top and sides were painted a drab khaki brown, relieved only by the Royal Flying Corps roundels on each side. The white painted aircraft identification letter, A to S for 18 aircraft with the letter I omitted, in front of each roundel, and behind the roundels, the squadron's identification symbol in white on the top and the sides. The service contract letter and number were painted in white or in black on a white rectangle near the tail, or sometimes on the fin. The streamlined steel tube undercarriage V-legs were not retractable. Their apexes were connected by 2 spreader rods of steel, and the whole structure was braced by 3 streamlined steel wires. Steel half axles, hinged at the centres of the spreader rods, carried a wire-spoked wheel at each outer end, giving them a track of 4.5 feet. Rubber elastic cord was wound over fittings on the outer apex of each V-leg and over each axle between the V-leg and the wheel bearing. This cord and the high-pressure 700 by 75 pneumatic tyres absorbed the shocks of takeoff, landing and taxiing. There were no brakes. The wheels were partly streamlined by fabric side covers. Port and starboard, the steel tube rear spar of the fixed tailplane was braced top and bottom to the rudder post by streamlined wires. The spruce front spar was similarly braced to the fin and bottom longerons. The tailplane ribs were of spruce, the leading and outer edges of steel tube. Try that again. The tailplane ribs were of spruce, the leading and outer edges of steel tube. Elevator, fin and rudder were steel tube frames. The elevator and rudder had steel strip ribs. Excepting the rudder, their fabric-covered surfaces were painted like the fuselage. The rudder bore the vertical blue, white and red stripes of the British identification on either side. The elevator was operated by single 1500 weight cables running above and below the tailplane on each side of the fuselage. The elevator was cut away in a V in the centre to allow for the movement of the rudder, but its port and starboard halves were interlocked, so that if any one cable was shot away, its duplicate on the other side of the fuselage would operate the complete elevator. The rudder was operated by 2 1500 weight cables on each side. The steel shod wood tail skid was sprung by rubber elastic cord and was steerable from the pilot's rudder bar through 14-gauge piano wire. You can just see the steel shoe on the wooden tail skid. The wings had 2 spars, all except the lower rear spars being milled into I section for lightness. Spars, ribs and compression struts were all of spruce. The wing structure was wire braced internally. The two lower planes were attached by rods passing through steel fittings at the junction of the bottom longerons with numbers 2 and 4 vertical struts and the fuselage compression struts corresponding to the wing spars. These two stout compression struts ran horizontally across the fuselage and formed the lower centre section of the wing structure. In the prototype Camel, the top wing was made in one piece, but in production machines it was divided into three parts. To carry the wide centre section of the top wing, which had an open window to improve the pilot's upward view, 4 streamlined spruce struts, cross-braced in front and on both sides, sloped upwards and outwards from the upper ends of the same fuselage vertical struts, whose lower ends accepted the undercarriage loads. Thus, a bad landing often slackened the centre section bracing, and if this were not attended to, trouble might ensue on the next or subsequent flight. Consequently, when I commanded an instructional flight group of Camels, every pupil was ordered to report each heavy landing, and my flight sergeant was instructed to have the centre section bracing checked after each flight, whether a pupil or an instructor had reported a bad landing or not. Perhaps it was partly through these precautions that we never had a Camel casualty despite ample aerobatics. The right and left upper planes were attached by fore and aft rods to the centre section spar fittings. 2 spruce streamlined interplane struts, adjusted and braced fore and aft by streamlined incidence wires, aligned the top and bottom planes outboard. Each spar was braced by double lifting and single landing streamline wires. Roundels were painted on the upper surface of the top planes and on the lower surface of the bottom planes and their ailerons. Their diameter was the chord of the wing. And the inner edges of the circles were aligned on the inner edges of the ailerons. Elsewhere, the upper surfaces were painted the same as the fuselage, but the under surfaces were painted a light colour to make the aircraft less readily seen against clouds and sky, and this lighter colour was also used on the bottom of the fuselage. Where the half-burnt castor oil covered up the light-coloured paint and gave you a more or less browny black fuselage underside, and also the root ends on the lower surface of the lower wings. The 4 ailerons were operated by a single 1500 weight cable which ran through the leading edge former ribs of the lower wings, then over a pulley in each wing and out of its undersurface to the lower aileron king posts. Upper and lower ailerons were interconnected by a streamline wire, and a 1500 weight balance cable from the top aileron king posts ran into the upper surface of the wings, over corresponding pulleys, and through the upper leading edge former ribs. You can just barely see the aileron horn there, and another aileron horn there with its wires. And there's another one, and there's an interconnecting wire. Late in the war, when seasoned spruce was scarce and aircraft were being built of brittle kiln-dried timber, one pilot took delight in diving Camels steeply and pulling them roughly out of the dive close to the ground. On some occasions he applied loads on the wings so severe that the lower front spars cracked and the lower wings bowed upwards at the front. He then flew around the aerodrome slowly, as if to exhibit his prowess, while the 1500 weight cable in the former ribs held his cracked spars in place until he landed. He received no blessings from the airfield aeroplane repair section. The engine was encircled by an aluminium cowl with a big circular opening at the front for cooling, and the bottom rear portion cut away to allow the exhaust gases and cooling air to escape below the engine mounting plate and under the fuselage. The 2-blade laminated walnut propeller was mounted immediately in front of the cowling without a spinner or any attempt at streamlining. Its pitch was non-adjustable. 2 installed Vickers machine guns weighed 70 pounds. Their two belts of 303-inch caliber ammunition, 31 pounds. Tracer, solid, armour-piercing, and sometimes phosphorus incendiary bullets were used in proportions laid down by regulations, or occasionally in accordance with a pilot's fancy. Tracer bullets were used to assist aiming. They also appeared to increase the chance that a stricken enemy machine would catch fire, even without the additional hazard of incendiary bullets. Either gun could be fired singly or both together by appropriately pressing two thumb triggers mounted side by side within the spade grip handle of the control column, but not until the pilot had loaded the breeches by means of a Highland loading handle, seen here and here, one for each gun, that made it easy to operate the cocking handle. The guns had Ferroto jam clearers, but a hammer was more effective. Pilots were expected to use their gun sights, and the standard Camel mounted both an Aldous tube sight and an open ring and bead sight. You can just see the ring of the ring and bead sight there. And this one has no Aldous telescopic sight. So we'll go back to the 4 Squadron Australian Flying Corps Camel, and it features a ring and bead sight on the right-hand gun, an Aldous telescopic sight, and a reverse ring and bead sight on the back end of the Aldous. Okay, photographic evidence. It is on record that one pilot added a reversed bead and ring because it looked more warlike and symmetrical. His Camel caught Major General Trenchard's eye when he visited the squadron, and it aroused his interest and enthusiasm. "This is what I like to see," he boomed to the squadron commander. "Shows a keen pilot who makes use of the equipment we give him." Perhaps in the general's mind was the thought that this scheme might be standardised for the whole corps. He turned to the pilot and asked him how he used his 3 sights. To his astonishment, the gallant and truthful youth replied, quote, "I never use any of them at all, sir. I just point my nose at the enemy, hose away, and hope for the best." Unquote. The Camel's guns fired through the air-screw disc, and either a Corper mechanical or a Constantinesco hydraulic interrupter gear stopped the guns when the air-screw blades were passing across their muzzles. The cockpit was open, and its simple Avro windscreen was just a flat sheet of non-bulletproof triplex glass mounted in an aluminium frame that pivoted fore and aft. Usually the Aldous sight extension rubber eye protector passed through a hole in the windscreen. The gun butts were just below the gun butts were in the cockpit just below the plywood coaming. In a nose-in crash, the pilot was thrown forward and only too often bashed his face against the gun butts. The resulting facial damage, broken nose was common, was seldom incurred without permanent disfigurement, and such unfortunate pilots were afterwards known as having a camel face. Even today I know some men who have the evidence of a camel crash imprinted upon their visage in a permanent compression of their normal frontal features. One is a well-known air correspondent in Fleet Street, Alan Tompkins, or JDS Allen, formerly of the Sunday Dispatch and later of the Evening News. The guns were fed from the magazines with the cartridges formed into a continuous belt by aluminium clips, which disintegrated and were an improvement on the earlier one-piece fabric reinforced with metal feed belts, which often wrinkled and so caused feed jams. The clips were discarded and ejected with the used cartridge cases down the ejector chute. The instruments were simple: an altimeter, engine revolution indicator, airspeed indicator, a cross-level or bubble inclimeter. Says we have a small compass, and there it is, right there in the centre. In theory, there's a watch. That's either a data plate or that's where the watch is supposed to be mounted. An air pressure feed air pressure gauge for the main petrol tank pressure feed, and a pulsator glass, as we mentioned, for the oil feed. The cockpit also contained a hand-operated fire extinguisher. I can't see the fire extinguisher either. Camel manoeuvrability demanded something new in safety belts. The early pre-war flyers had flown without any, some of them lying or sitting on the wings without even a nacelle to protect them. When the Frenchman old-fadhioned first introduced the loop to an astonished world in 1913, he simultaneously introduced the necessity for safety belts. When the Camel first appeared, it was fitted with an abdomen belt about 4 inches wide and attached to the rear support for the seat. The first one I encountered had elastic sides, presumably for comfort. But if one pushed the stick forward, its response was so swift that the pilot was shot forward and upward when the aeroplane shot downward in a dive. The elastic-sided belt then expanded and allowed the pilot to slip through its embrace. On one occasion, I was thrown out of the cockpit and found myself lying on top of the gun barrels, with my nose perilously close to the whirling propeller. Pilots soon overcame that danger by turning the Camel over sideways to start a dive. But even so, some better safety device was necessary. It was then that Captain Oliver M. Sutton invented the Sutton harness. This had 4 straps, 2 of which came across the top of the thighs and 2 over the shoulders. All 4 straps had metal reinforced holes of close pitch. The appropriate holes in these straps were passed over a conical steel pin, and a spring clip was then pushed across the top strap through a hole in the pin. The pilot was then securely held in any attitude of the aeroplane, yet he could release himself quickly by merely withdrawing the clip. The harness of today is simply an improved version of the Sutton harness, but the name of Sutton is long forgotten by all but pilots of the First World War. Sutton, who won the Military Cross in that war, received scant credit and no recompense for his practical solution to the problem of belted safety for the pilot. The inclinometer was merely a glass tube spirit level, slightly curved instead of straight, and set in an aluminium frame marked off in angles of 5, 10, 15, 20 degrees. It was mounted across the aeroplane in the centre of the instrument board, slightly off-centre. It was the progenitor of instrument flying. Its function was to indicate side slip when flying level or turning. Perfect flying, of course, maintained the bubble always equally divided by the line marking the exact centre of the instrument. Like the ordinary spirit level, it was a precision instrument, which was all very well for instructing novices and for peaceful flying, but it was valueless in combat, when one flew according to the exigencies of the moment and there was no time to look at instruments. The air bubble was the only moving part, and the inclinometer's life was infinite unless its glass were broken. But one wag who prided himself on his flying sent in an official request for a new inclinometer, on the grounds that his old one was worn out in the centre. In addition to fighting, the Camel was used as a fighter bomber and ground assault aircraft. It was flown from warships. Sopwith Camel taking off from a warship. A fellow by the name of E. Dunning, squadron commander, on the 2nd of August 1917 on HMS Furious, and this is where he's landing. The people going out there to grab a hold of the aeroplane, that's what he had instead of an arrestor wire. Sopwith Camel was used, carried by airships, and air-launched as the airship's fighter escort. Well, what do you know? There's a Camel with its inclinometer in the centre of the panel, just as the description said. On 19 July 1918, 7 Camels took off from the Furious aircraft carrier, each carrying 2 50-pound bombs. They destroyed 2 Zeppelins in their hangar at Tondern, 80 miles away. On the 11th of August 1918, a single Camel took off from a lighter towed by a destroyer in the Heligoland Bight and from nearly 19,000 feet shot down in flames the last Zeppelin to fall in war. This, then, was the Camel, of which 5,490 were built in 1917 and 1980. By far the greatest number were Clerget-engined. Next came those with Lirone or Gnome monosoupape engines, and a much smaller number with Bentley engines. There was a special naval version designated 2F1 for shipboard use, with 13 inches smaller span and a fuselage that could be quickly detached at the number 5 struts for easy stowage. There were other differences from the F1 Camel, and of these the most important was the removal of the starboard Vickers machine gun and substitution of a Lewis machine gun on a Foster mounting on the centre section of the top plane, which enabled the rear end of the gun to be pulled down for changing ammunition drums and for firing upwards when attacking Zeppelin airships from below. There was also, this is not in that book, there was a night fighter version, and for the night fighter version, what they did was they swapped the fuel tank and the pilot's cockpit. They put the pilot back here so that he could then pull the gun down from the top wing and play around with it. And it also gave him better protection from the gun muzzle flash blast, which would otherwise night blind him. But anyway, better get back to the scripted text. The Camel was easy to make and assemble by any firm which could handle timber, make small metal parts, operate a tinsmith shop, cut, sew, paint, and dope fabric, and produce skilled riggers and engineers for assembly work and inspection. So, in addition to the parent company, the F1 Camel was made by Hooper and Company, the British Caudron Company, and the Newport and General Engineering Company, all of London, by Ruston, Proctor and Company, and Clayton and Shuttleworth, both of Lincoln, Marsh Jones and Cribb of Leeds, Portholme Aerodrome, Huntingdon, Bolton and Paul Norwich, not all of whom had made aeroplanes before. In addition, William Beardmore and Company of Dalmuir built 2 F1 Camels, the naval version. Today, when a modern fighter aircraft costs anything from £120,000 to £300,000, 2020 prices, and Lockheed F-35 Lightning goes for 150 million Australian dollars, and prospective American types may cost $3 million, it is remarkable to look back and discover that the Camel F1 airframe cost £874 and 10 shillings, and the 2F1 cost £825. The airscrew, instruments, guns and sights are not included because these items were bought separately and supplied to the airframe makers. The Clerget engine was the most expensive of the rotary engines. At £907, 10 shillings, it cost more than the airframe. Probably the complete aircraft ready for combat cost just a little more than £2,000. For the price of the 5,490 camels of the First World War, the nation today would get many fewer than 100 modern fighters equipped for today's operational squadrons. And I did the calculation, and it turns out that if you went to New Zealand and paid them $500,000 for a new build Sopwith Camel just like this one, with a new build rotary air engine, you could get 300 Sopwith Camels for the price of one F-35 Lockheed Lightning fighter. Australia's going to buy 75 of them at $150 million each. Don't you think we could frighten the Indonesians more if we had thousands of Sopwith Camels to defend the borders of our island continent? Just a thought. And that thought brings me to the conclusion of Camel Warble video number 2, which brings us to the conclusion of the original material from the 1960 edition of Great Aircraft by Captain Norman Macmillan. The third video in this camel-centric series, we'll have a look at what modern aerodynamics and aeronautical engineering has to say about the layout of the camel how they achieved what they wanted to achieve, which was an aeroplane that would be hard to shoot down, because they were sick of aeroplanes that were easy to shoot down because they'd been designed and built to be easy to fly, and therefore you couldn't take evasive action in them. You were better off getting up and running around outside the cockpit of a BE-2C or an RE-8 than trying to actually aerobat the aeroplane. Anyway, that's for the third video. Warbles on a lot to YouTube. 1,250 to 1,300 RPM, and at full throttle in a dive, you run them up to 1,500 RPM and their insides would melt and drip. I wish I had one to play with. Warbles on a lot to YouTube. Ciao.